regression at least. So I hope this video was helpful. In the next video, we're going to talk a little bit about how we compute and determine these regressions. We'll see you there. Okay, let's go ahead and talk about how we compute these regressions. So the first thing that we've done all term, the first thing we got to do that we've talked about all term, how many people do we need to do this study? And so we go back to our tool set here with G-Power, and because we are trying to test whether the line of best fit is a good line, and we need to use the ANOVA in order to determine whether that line is a good line, well, we're going to go back to the F family. And so we're going to make sure that the test family is selected as F, and the specific kind of statistical tool that you want to use in this case is what's known as a linear multiple regression. This is a design flaw with G-Power. We are doing it right now in terms of bivariate regression, but this can be done with multiple regression. So we're talking right now, just from an introductory statistics point of view, on what happens when we use one predictor and one outcome variable, but this particular tool needs to be adaptable for multiple regression studies where you have more than one predictor variable in one criterion variable of interest. And so even though it says linear multiple regression, it's completely fine. We can use it for bivariate regression as well. So we're going to go ahead and use the a priori type of power analysis, which we've used all term, because we want to know how many people do I need to collect X and Y data on in order to generate this regression equation. I'll leave my effect size alone, make sure my alpha level stays at 0.05 like we've been using all term, and my power threshold remains at 80%. Now, the key difference here between bivariate regression and multiple regression is based off of the number of predictors that you would enter into the model. And so when you have one X predictor, I typed in the number 1. But if I was doing multiple regression with 2, 3, and 4 predictors, of course, I would put 2, 3, or 4 into that particular value and click the calculate button. So because I'm doing bivariate regression and I'm interested in one predictor and one criterion, I only have one predictor. And so when I do that, you can see that it gives me an F critical value of 4.023. And the sample size that I need to successfully conduct this type of experiment is 55 participants. So that means I need 55 people where I measure X and Y value in order to do this successfully. So that's power analysis. The reason why a bivariate regression is the right tool to answer this kind of a research question is because the intention of my project is to determine or to use a prediction formula to guess or estimate my Y criterion variable of interest from a single X predictor. And so because I want to predict something that I don't know about, and that's Y, and I have one X predictor, bivariate regression is appropriate. The second thing to think about is because my X and Y variable are trying to predict each other, and we assume that there's a linear correlation between them, I therefore need to ensure that both my X and my Y variable of interest are at least interval or ratio level of measurement. Yes, you can use categorical variables. I know I said that earlier in the lecture videos, but ideally, the purest way that this is done is with continuous data only. So those are my reasons for this. So our statistical hypotheses would start with the null and the alternate hypotheses, just like we've done all term. So the null hypothesis would declare that there's no significant relationship between the Y criterion and the X predictor in a Z given population. The alternate, of course, would then state that there will be a linear relationship and there will be, therefore, a linear prediction between my Y criterion and my X predictor in Z. The substantive hypothesis is going to stay exactly the same, right? This is what you think as an educated guess being the researcher. And so you might think, based off of theory and logic or information you read from a literature review, that Y will be linear predicted from X. And symbolically, you would represent the null and the alternate hypothesis by saying Y predicted will be equal or not statistically different from giving the unknown value the Y average. And the alternate hypothesis, or H1, would be that the Y predicted does not equal the Y mean, meaning there's a statistically significant difference in the regression line, and that regression line is better capable of estimating that Y variable of interest than the Y mean. And so these are our hypotheses. Given that we are using our F distribution, we're going to go back and use this positively skewed F distribution that we talked about with the ANOVAs. And then we need to determine the critical value. And so just like how we had k minus 1 and n minus k, we need to use those same degrees of freedom strategically in how we determine the critical value for our bivariate regression. And so in this particular case, the numerator, which we defined as k minus 1 for ANOVA, in this case, k represents the number of predictors. And so because I have two variables, an x and a y, minus 1 restriction, that's going to be 1. And then for my denominator, it's going to be n total sample size minus k number of predictors minus 1. And so that's the difference between regression and ANOVA, is that in ANOVA we used n minus k, but in regression we use n minus k minus 1. So if we look at our table here and we say that our numerator is k minus 1, we're going to look at this one column, right? Because we only have one predictor. So two variables minus one predictor is 1. And then n minus k minus 1, if we were to say 55 minus 1 is 54, and then minus 1 additional degree of freedom would be 53, you would find the coordinates, which isn't shown on this slide, but you would find the point at which that intersected on this F critical table at the 0.05 level, and you would find the specific F critical value that you're going to be comparing your calculated F observed value to. So that's how you find the critical value with the F table. In terms of calculating the process for this line of best fit and determining the degrees of freedom, you need to use these 13 steps in order to calculate them. And so we will do some live demonstrations in class, and we'll have some videos for those of you joining us in the online only environment. But this process is really important that you don't skip steps. And so we will walk you through this step by step, but you'll want to refer back to this formula sheet as we move through the calculation of our regression analysis. Okay, so keep that in mind. And then the last thing, as I said before in an earlier video, is that once we determine the F statistic, that is based off of parametric statistical probabilities at a 0.05 alpha level with 95% confidence. But sometimes we need to just understand what an effect size is. And so in this particular case, as we mentioned, we're going to go with the R squared to represent the effect size metric, the degree to which the predictor and the Y criterion are impacted upon each other, regardless of whether the alpha level is or is not statistically significant. And so when you do this effect size calculation, we're going to look at the percentage of Y that is explained by X and the percentage of X that is explained by Y. And so this doesn't infer causality. This just merely means the two variables are related and gives us a sense of how much of the total variability is accounted for between the variables. So then to walk through our statement of the finding, right, we would state that bivariate regression analysis was used to test if X significantly predicted Y. The results of the regression indicated that the X predictor explained a certain percentage, whatever that percentage may be, of the variance in Y. Provide your R squared, your F statistic, and your degrees of freedom for the numerator, and your denominator with the p-value. You would then conclude by stating that X significantly predicted Y and provide the beta slope, so it could be standardized to other samples in the population, and the p-value. So to conclude, you would simply state that the X predictor predicts or does not predict the Y criterion, which answers your research question. So I hope this video was helpful. In the last video, we're going to talk a little bit about non-parametric. What happens if we violate the basic assumptions for regression and need to come up with an alternative plan to try to estimate our unknown Y variable of interest from an X predictor non-parametrically. So we'll see you there.